Hello, my name is Matthew Farmbach. I'm a senior structural engineer at HDR, and I'm honored to be able to present to you today the Penn Medicine Pavilion project on behalf of our integrated project delivery team, Penn First. Before jumping into the solutions, a quick recap. The Pavilion is a 1.5 million square foot hospital located in the University City section of West Philadelphia, just on the edge of University of Pennsylvania's campus. The all-steel superstructure is approximately 322 feet tall, and the 6-story precast parking structure extends 67 feet below street level. The total construction cost was $1.1 billion. The hospital had a number of key requirements for the new building, listed here. The biggest drivers for the structural design were the top two: the number of private patient rooms and the requirement for on-site parking. The long, narrow, urban site is located in between two adjacent hospitals, the Penn Museum and the SEPTA light rail station to the south. The only way to fit 1.5 million square feet of program space and a 690-stall parking garage on the site was to use every single square foot of the property below grade and to go vertical above grade. The building is big, but the site connections, pedestrian bridges, green spaces, and pathways are meant to break the building down into a more manageable scale. In section, the patient floors and interventional floors are sandwiched by an upper and lower mechanical room level, with lobby, public amenity, and the emergency department sitting below the lower mechanical room on the first two levels. A loading dock sits below the northern third of the tower, while the 6-story parking garage supports the south half of the tower. A number of innovative solutions were discussed in our award submission, but given the short time that we have today, I'm going to focus on two areas. First, the structural steel designed to accommodate the underground precast parking structure, and second, the 50-foot cantilever. This aerial view shows the building that previously occupied the lot. The 5-story concrete parking structure would have to be replaced, plus additional parking for the increased number of patients, staff, and campus traffic. The integrated project delivery team studied several different types of parking structures, but ultimately selected a precast structure due to the long spans and the speed of erection. The column grid for the garage was roughly twice that as the tower above. You can see how the tower's column grid overlays onto the parking garage. The red X's indicate where a column was required to be transferred. In total, nearly half the columns needed to be moved onto a new grid before they reached the parking structure. One important thing to note, the elevator core columns were able to remain continuous down to the mat foundation below, while the brace frames within the elevator core transferred their lateral forces into the precast shear walls at the top of the parking garage. The column transfer strategy was twofold: transfer the exterior columns within the double-height mid-level mechanical room, and transfer the interior columns on the public level just below the mechanical room. For the exterior column transfer trusses, a continuous top and bottom cord, location shown in red, tied the diagonal columns together. Large column sections were used for the diagonal sloping members, with their flanges turned outward to match the vertical column orientation. This kept the largest unbraced length on the diagonal member's strong axis. Weak axis bracing was provided at the sloping column's midpoint, further economizing the design. Typical gusset connections for the transfer trusses are fully bolted, up to 1¼ A490 bolts in a staggered pattern. The holes in the gusset plate provide a hand-hole access point for erectors. These holes were later filled completely where required for the gusset design. The more regularly spaced continuous transfer truss on the east side extends nearly halfway down the building's length. One thing to note is the column connecting to each truss high point switches from compression above the truss to tension below, and hangs the lower floors down to the parking garage. This reduced the steel tonnage on the lower floors since long span girders were not required. Here's a close-up view of the full transfer truss connection on the east side. The interior trusses follow a similar design pattern, however the member sizes are larger because we didn't have the truss depth or continuity that the mid-level mechanical room afforded. The column and diagonal shapes were cover-plated W14 by 730s. We originally specified W14 by 808 and 873s on the drawings, however the steel fabricator indicated that it would be faster and less expensive to cover plate the W14 by 730s, which were domestically readily available. These two interior transfer trusses and their connections are similar in configuration to the exterior trusses, just with larger members and connections. The construction team had completed nearly 30% of the precast parking structure and steel erection to start on the north side of the site when the design team received a proposed design change to two of the interior transfer trusses. The design team worked side by side with the fabricator to repurpose steel already purchased and in some cases detailed in the fabrication shop into a new truss configuration that would align with the hospital's needs. In the end, Almost all of the steel was able to be repurposed from the original design. Given the size of the hospital and its prominent location on campus, the designers looked for different ways to break down the scale of the building through the use of green spaces, pedestrian walkways, and an elegant glass facade. The overall building footprint was largely driven by the required size of the typical patient floor, which was a fixed element in the design. Bringing this footprint straight down onto the site would have significantly reduced the amount of space at ground level for the green spaces and pedestrian paths. By cantilevering out the building's northernmost 50 feet, and cantilevering out 10 feet all the way around the building, the team was able to significantly increase the space at grade. The diagram on the right shows just how much public green space we were able to maintain by cantilevering the building. The soffit of the cantilever is over 60 feet in the air, and it lifts the building up out of the public view from grade. The red columns from the patient floors needed to be transferred onto the two circled purple columns in order to meet the design intent. This meant that the entire area shaded in green would need to be supported somehow on floors 3 through 16. The integrated project delivery team studied several different options, taking both cost and constructability into consideration. Ultimately, the team selected a multiple truss scheme to support the cantilevered area. Within the upper mechanical room, a bent transfer truss follows the northern exterior facade, and below the third floor, hidden within the soffit, are two 11-foot deep transfer trusses. An additional W-shaped truss between the third and fourth floor, perpendicular to the lower main trusses, transfers the 3-column pattern from the tower above to the 2 columns below. The 2 columns shown in blue were dubbed the super columns. These 2 built-up columns are comprised of 4-inch thick grade 50 plates, compositely cast with 10 KSI concrete. Each column supports over 10,000 kips of factored load. The upper and lower trusses support separate vertical zones. The upper truss supports floors 10 through 16 in tension, while the lower trusses support floors 3 through 9 in compression. Each truss was cambered up the required amount for it to be level after all slabs were poured. Between the 9th and the 10th floor, the column essentially sees no load, as it is the point in which the column switched from tension to compression. The columns were tied together to meet the code-prescribed tension requirements for column splices, as well as to allow the building to move together for transient loading. A closer look at the lower truss shows the compression columns in purple, the primary trusses in red, and the W truss in green. You notice that there is a 10-foot section where the green W truss and the red trusses come together before the load is then transferred down to the composite columns below. This connection was studied extensively by the team. With such a large amount of load coming together at one point, the connection had to be robust enough to meet all of the load demands while also being easily transportable and erectable. It was important that the connection stay below a specific weight limit so that it could be erected by the tower crane. Otherwise, an additional crane would need to be placed on the street and the street closed off. This would have caused an incredible amount of disruption to the hospital. The fully bolted connection shown was the result of the team's careful study. It allowed the entire truss to be bolted into place, creating splice points in members with compression. The entire lower truss assembly was erected in the fabrication shop prior to being shipped to the site to ensure that it could be erected with minimal adjustments needed in the field. A closer look at the upper truss shows the extent of the cantilever truss members. The mechanical room is 27 feet floor to floor, which drastically reduced the weight of the truss. The blue highlighted members are struts that were positioned to take the out-of-plane forces that result from the truss not being orthogonal. These struts engage the concrete diaphragm with shear studs to transmit the lateral forces back to the brace frame cores. Photos taken midway through steel erection show the extent of the lower trusses on the left and the cantilevered structure erected up to level 9 on the right. Close-up views of the steel node at the bottom of the lower trusses show the amount of field bolting required to erect the trusses. The composite columns below, at this point, have not yet been formed or poured at this stage. Here's a view of the third floor looking out onto the cantilever through the W truss. Stiffener plates in the horizontal beam at the fourth floor help guide the column flange forces down to the diagonal members below. The construction sequence for the cantilever was proposed by HDR based on the findings of a stage construction analysis. The sequence ensures that the structure is loaded in the proper order, allowing members to be stressed consistent with that analysis. This sequence was shared with the fabricator, erector, and the contractor for coordination and further refinement based on their feedback. Understanding of this sequence by the entire project team allowed the curtain wall to be erected on the partially completed cantilever, resulted in a project schedule savings. The cantilever structure was surveyed after each slab pour to check that the camper was coming out as anticipated. On behalf of the integrated project delivery team, Penn First, thank you for the opportunity to be able to share this incredible project.